Here in Chapter 12, we'll be looking at analysis of variance. And in this case, we'll be focusing on the one-way ANOVA. So what is analysis of variance? So it's a method for testing the equality of 3 or more population means by analyzing sample variances. So it'll be a way for us to distinguish between different samples and determine whether or not these different samples come from populations with different means. So we've kind of looked at this similar idea when we're comparing the mean between two samples, but now we're going to apply this idea to more than two samples. So for instance, if we want to compare 3 or more samples. So one-way ANOVA is used with data categorized with one factor. So there is one characteristic used to separate the sample data into 3 categories. Into the different categories. So what are the hypotheses going to look like? So the null hypothesis will be that all the means from each sample come from populations with equal means. So for instance, if I have 3 samples, then our null hypothesis would be that mu1 is equal to mu2 is equal to mu3. Or maybe I have more than 3, so you can imagine that there would be an equation that says that all the means, all the mu's are equal to each other. And the alternative hypothesis is that one of those means is not equal to the others, or at least one of those means. So at least one of the means is different would be the conclusion that we would draw if we were to, for instance, reject the null hypothesis. So what will this process come down to? Well, for the case when we compare the different sample means, and it looks like all the sample means are close to each other, then we would not be able to reject the null hypothesis. We would have to fail to reject. But if it looks like at least one of them is different from the others, says that all of the xk's are all the sample means are far apart, would actually not be necessary. You would only just need one of them to be significantly different from the others, and that would be enough to reject the null hypothesis. So here's an overview or a breakdown of the strategy for hypothesis testing with analysis of variance. So first, we're going to have several samples where each sample that we're taking comes from a population that's normally distributed, and their populations have the same variance. The samples are independent, simple, random samples with a level of significance here will denote alpha. And like we mentioned earlier, the null hypothesis is that all the means are equal. So in this case, we would be looking at a case where we have k different samples, and at least one of the means is different from the others is our alternative hypothesis. We'll see down below that the distribution that we're using is the F distribution, and it'll always, when we're computing the p-value, it'll always be a right-tailed p-value. And here's a breakdown of the various components that go into computing the test statistic. So don't be too scared off by these formulas, because for the most part we're going to not need to know these formulas. But just to get an idea of what these formulas do, let's break it down a little bit. Now in this this first box here, where they're looking at the what they call the factor, we're looking at the sum of the squares here, which is denoted SS. And what this computes here is it takes each of the means of each sample, which we're denoting x bar j, and subtracting that from the mean between the samples, and multiplying, and then summing those up and then multiplying by n. And then when we divide that by k minus 1, what we wind up with is this factor here divided by k minus 1 gives us the standard deviation between the sample means, and then multiplying it by n. So really what this amounts to is n times, so n being the sample size of each of our samples, times the standard deviation between the sample means. And I'm actually, sorry, I'm misusing that's not the right, it's the variance between, not the standard deviation, it's the variance between the sample means. In other words, the x bars. So we'll multiply n times the variance between the sample means. What's going on in this one here? Well, this is looking at the what they're calling the error. So we're summing up each of the data values from our samples minus the corresponding sample mean, squaring that, summing. And then over here, when we divide, this is called the sum of the squares, or SS for the error. When we divide that by n minus 1, what that gives me is the standard deviation of that particular sample, or I'm sorry, the variance of that sample. And then we're going to sum that up between each of the different samples, and then divide by k. So what that does is it takes the mean of each of the sample variances. So that's what this is really. It's the mean of the sample variances. So then when we divide each of those, we get the F score, which is our test statistic. So sort of how we were stating up here, the MS factor, the mean squares of the factor, will be the variance between the samples, right? So it's the variance between the different x bars, and then timesing it by n. And then the mean squares of the error will be the variance within the samples. So here, the way I was saying it, it's the mean of the sample variances. Okay, so that's going to be how you compute the F statistic, and it's going to be on a distribution that looks sort of like a skewed right distribution, a little bit different than the chi-squared distribution, and we'll be using the FCDF to compute the area under it. Although, for the most part, I'm going to avoid having to do it this way because it involves a lot of various different formulas. We can do this all using just one calculator function, using the ANOVA function. So in other words, all this can be skipped here if we just go straight to ANOVA. And then you enter the different lists into the ANOVA function, and then it gives you everything you need. It gives you the test statistic, and it gives you the p-value. So in fact, we'll see in a moment that, yeah, doing it this way with all these different formulas amounts to a lot of work that's not necessary.